Okay, let's dive into this. Welcome everyone to today's Explainer. Have you ever looked up at those massive steel towers, or even just the wooden poles crisscrossing our neighborhoods, and wondered how all that raw, literally lethal electrical power stays exactly where it's supposed to? Well, today, we're exploring the absolutely fascinating world of power line insulators. These are the silent grid guardians that make our entire modern electrical infrastructure possible. We're going to break down the incredible engineering that goes into these devices. Because, it might look from the ground like just a simple chunk of ceramic or glass, but actually scratch that. As we're about to see, there is a brilliant, highly specific science behind every single shape up there on the wires.
So here is our roadmap for today. First, we'll look at the silent grid guardians themselves. Second, managing high voltage heavyweights. Third, handling tension and angles. Fourth, local power and specialized gear. And finally, we'll wrap up with modern materials and a pretty massive misconception.
All right, part one, the silent grid guardians.
At its very core, an insulator serves an absolutely crucial dual purpose. And I want you to really focus on this dual purpose. An insulator is used in power systems to provide electrical insulation, right, but also mechanical support to the conductors. This is the big takeaway here. They don't just stop electricity from taking a shortcut down the pole and into the ground. They physically hold the entire grid together. I mean, think about it. Those conductor lines carry immense weight, especially over long distances or when they get coated in heavy winter ice. If an insulator fails mechanically, the line physically drops to the ground. If it fails electrically, the power just shorts out. It literally has to perfectly execute both of these intense jobs simultaneously 24/7, no days off.
Now, what's really interesting about this slide is the sheer, wild variety of solutions engineers have come up with to fulfill that dual purpose. Look at this. This chart showcases 11 key types of power grid insulators, and you'll notice they all look totally different. Some look like stacked ribbon mushrooms, others look like strings of glass discs, and some just look like solid barrels. This vast array of shapes and sizes isn't just for, looking cool. It all stems from solving highly specific engineering challenges based on the voltage level, the physical location, and the environmental stress. Let's decode this together.
Moving on to part two, managing high voltage heavyweights.
Let's see exactly how voltage dictates design by comparing two of the most common types you'll see out there, the pin insulator and the suspension insulator. The magic dividing line here, 33 kilovolts. The pin insulator, which has that classic tiered, almost mushroom-like shape, is mounted securely on a pin fixed directly to the crossarm of the pole. It's incredibly effective, sure, but it is strictly used for distribution lines carrying up to 33 kV. Once you cross that 33 kV threshold, the physical demands just change completely. That's where the suspension insulator steps in. Used for voltages above 33 kV, this isn't just a single rigid piece. Instead, it's a hanging string of disc insulators. It's brilliant, because by stringing them together, engineers can just add more discs to handle higher and higher voltages. It gives them massive flexibility on those giant transmission towers.
But okay, what happens when you need high voltage insulation combined with rigid, unmoving support right from the ground up? Enter the post insulator. Unlike those hanging suspension strings we just talked about, post insulators look like thick, sturdy columns. They are specifically used in substations and on high voltage lines where you need absolutely rock-solid stability. They provide the extreme mechanical support needed to keep heavy, dangerous equipment firmly in place while making sure all that high voltage stays completely isolated.
All right, part three, handling tension and angles.
So the crucial point is that when a power line has to abruptly stop or turn a really sharp corner or, say, cross a massive gap like a river, the physical strain on the line is just off the charts. Enter the strain insulator. Its applications include dead-end towers, river crossings, and sharp angle towers. Physically, it looks a whole lot like the suspension insulator we discussed earlier, using those same basic disc units. But here is the genius adaptation. Instead of hanging vertically, it usually consists of disc insulator strings placed horizontally. It is literally pulling against the extreme physical strain of the wire, kind of like an anchor in a giant game of tug-of-war, while still blocking that massive electrical current.
Now, down at the local low-voltage distribution level, we see some totally different tension solutions. Take the shackle insulator. It's this stout, round unit used in low-voltage distribution lines, and it's super unique because it can be mounted either horizontally or vertically depending on the angle the wire needs to take. We also have the brilliantly designed stay or egg insulator.
You've probably seen wires anchoring utility poles to the ground, right? Those are called stay or guy wires. The egg insulator is placed smack in the middle of that wire. Why? Because if the pole becomes accidentally electrified, this little egg prevents that deadly leakage current from traveling down the wire and reaching the ground. It literally protects anyone who might just be walking by on the sidewalk.
Which brings us to part 4, local power and specialized gear.
Whenever you see those large metal cans up on poles or those massive ground-level green boxes in your neighborhood, you're looking at transformers. But think about it. How do you get a supercharged live wire into a metal box without electrifying the whole box and blowing it up? That is exactly where the transformer bushing comes in. This highly specialized insulator allows a conductor to pass safely straight through a transformer tank. It basically provides a robust collar of insulation right between the live conductor and the metal tank wall, ensuring the electricity does its work inside without turning the whole setup into a hazard.
And you know, insulators aren't just out in the elements either. Let's look at this incredibly niche but vital application, the ESP insulator. ESP stands for electrostatic precipitator. It's a piece of pollution control equipment used inside thermal power plants. These insulators are used specifically to electrically isolate the collecting electrodes inside these massive industrial facilities. It just goes to show how the core concept of the insulator is adapted for extreme, highly specialized indoor industrial environments, not just hanging from towers in the rain.
Finally, part 5, modern materials and misconceptions.
And this brilliantly illustrates how material science plays just as big a role as physical shape. The basic unit used to make those suspension and string strings, the disc insulator, can be manufactured from 3 totally different materials depending on what the engineers actually need. First is porcelain. That's the classic, traditional base material that has been used for decades. But look at toughened glass. Why on earth use glass? Because when glass takes damage, it shatters clearly. This means when maintenance crews are inspecting miles and miles of lines, damage is clearly visible from a distance, which saves immense time and money. Finally, we have composite or polymer insulators. These are widely used in modern transmission lines because they are incredibly lightweight and highly pollution resistant. They literally repel water and grime that could otherwise create a path for electricity to escape.
Now, we're going to wrap up this explainer with a question that trips up a lot of people who are just getting into electrical infrastructure. You'll often see other devices mounted right near insulators, on poles and towers, and a common one looks very, very similar to an insulator. So, I pose this question to you. Is a lightning arrestor an insulator?
The answer, straight from our engineering source material, is a resounding no. Lightning arrestor is not an insulator. It is a surge protection device. While an insulator's entire job is to stop electricity from flowing to the ground at all times, a lightning arrestor is designed to intentionally direct sudden, massive spikes of electricity, like a literal lightning strike, safely into the ground to protect the equipment. They look super similar, but their jobs are entirely different. Next time you pass by a power pole, look up. Try to spot the pin insulators, the suspension strings, or those little egg insulators on the stay wires. Which one of these silent guardians do you think has the toughest job? Think about that and keep exploring the amazing engineering all around us. Thanks for joining me on this explainer.